In this video, I'm going to talk about vector calculus. So what is vector calculus? So vector calculus is similar to the scalar calculus, except that we're talking about vectors instead of scalars. For example, if I talk about scalar calculus, I talk about a function f of t, which is a scalar, and this function is with respect to the variable t. For example, if I give you the ft, which is t squared plus t, is a scalar function, I can actually compute the limit, the derivative, the integration, so on and so forth for the scalar function, which is called scalar calculus. So the vector calculus talks about a little bit general sense. When we have a function, a vector function, which means I have a vector which is function of t. Okay, of course, because of vectors, we have a numerous elements in the vector, and each element actually is a function of t. Okay, for example, if v sub t vector, which is composed of two elements, which is v1t, v2t, and in particular v1t is t squared plus t, and v2t is t plus 1, so this is my vector function. Okay, for this one, I also can do the vector calculus. For example, I can do the limit, say the limit as t go to 5 of this v sub t. So what you do is you just do for the individual element in this vector function, you compute the limit. Okay, for example, I compute the limit of v1t as t goes to 5 and limit of v2t as t goes to 5. So you can compute the actual value. So without going into detail about the compute limits, so you actually compute limits for the first one, v1t will be 30 and v2t will be 6. Okay, so that's why you compute limit. So similarly, you can compute the actual derivative of the vector with respect to t, of course. So which will be v1t, you just the same way, same principle, you just do the derivative of each individual element in this vt, and you take that one with take that derivative with respect to dt, so you get the derivative. Okay, which means I have v1t dot and v2t dot. So if you take these two functions, the v1t dot will be the derivative of t squared plus t over dt, which gives us 2t plus 1. And the derivative of v2t over dt will be just derivative of t plus 1 over dt, which just give us 1. Okay? So you can also talk about the integration. You can also do the integration of ft. I didn't include it over here. This is 0 to 5 somehow dt. Okay? You can also do the integration of 0 to 5 vt dt. So again, this will be just each individual component. Okay, just this 0 to 5, the v1t will be just t squared plus t dt. This guy will be integration 0 to t plus 1 dt. So that's still, you just do integration for each individual component. Okay, all right, let's talk a little bit about the gradient as a derivative, because the derivative is a little bit more useful in many applications. So of course, the integration you can also can be also very useful. Okay, so the derivative, let's say the derivative of the scalar function has some physical meaning, which means it's a change rate of ft with respect to the variable t. So which means as t, if I want to draw over here, okay, this is my t, this is f of t. Okay, somehow like this. So actually this derivative talks about how fast ft will change. Let's say this is my t, some value over here. I'm going to change this t a little bit, tiny little bit, how my ft will change. That's what the derivative means. Okay, so I give example over here showing that what that means in terms of derivative. Okay, so similarly for the scalar as a vector, we also have some physical meaning. So it's a little bit different from the previous one, for the scalar one. So if you look at the derivative, the derivative of this vt with respect to dt is sort of, you can, by using physical meaning, it's just given by v vector of t plus delta t. So delta is pretty small number minus vt itself and divided by delta t. So it actually characterizes the change rate of the v sub t. It's similar to this one. The only difference is this is a vector, which means it actually try to figure the change rate of v sub t in terms of both sides, magnitude and the direction. Okay, this one only talk about magnitude. That's the difference. So if I take a derivative of that, so if I give example over here, this v t plus delta t is this purple one, and vt is the blue one. So the difference, actually, if you do the minus, actually that's the red one. Okay. So let's actually talk about how the vector change, the change rate of vector after we increase this t by a little tiny bit. Okay. So again, the calculation wise, you just do the integration of each individual component with respect to t, as I mentioned over here. Okay, right over here. So you can do that, calculate in that way. So the physical meaning is change rate of the v sub t in terms of both size and direction. Okay. So I'm going to give you an idea about what that means. Let's see if I have v sub t, which is cosine t, sine t. Okay. So if I look at the v sub t, okay, if you look at v sub t when t is 0, okay, when t is 0, so my v sub t is right over here. When t is 0, my v sub t, if I replace t by 0, I have cosine 0, which is 1, and sine 0, which is 0. So this is 0. So this is this point, okay? So this point. Now, if I take the derivative, I'm going to calculate the derivative of when t is 0. Derivative is, I take a derivative of this each individual component, element with respect to t. So I have a negative sine t, which is derivative of cosine t with respect to t. And I have a cosine t, which is derivative of sine t with respect to t. So if we let t be 0, so I have v dot t at t equals 0 is 0, 1. If I draw that one, 0, 1 is 0, 1. You go up. Actually, you're going up. It's this vector. This vector, okay, I'm drawing this vector. This vector is you're from x-axis 0, okay, y-axis is 1. So it's going up, right? Because vector, you can shift it. So it means at this point, the derivative is going up. Okay, as you can see, yeah, it is, because if you draw it out, you can see as t increases, you're actually moving along the circle. Basically, your vt is moving along the circle, so which means going up. Yes, indeed, the velocity going up. So as you can see, even if my point is over here, but actually I'm moving up, it may not have the same direction as my vector itself. Okay, the vector itself is this guy. The vector for this guy. For this guy, 1, 0 is this, okay? But its derivative is going up, so which will make sense in this case because you are moving along the circle, so you go always as you move the t a little bit, it's going to move up. That's why the velocity is going up. The color is going up. The change rate is going up. Okay. You can also compute the same way when you're on top over here. When t is pi over 2, okay. So the actual vector is this. This is actual vector. This is actual vector is this. So when you take a derivative, when you take actually the derivative of this, when t is pi over 2, the change rate of this vector is actually moving to the left. Okay, if you do that, which does not make sense because as t increases, you are going to move along the circle. That's why at this point you're going to move to the left. Okay. So again, I will emphasize this is the meaning of the derivative v dot t is the change rate of vt, which includes both size and direction because we're talking about vector. Okay, so in my previous video, I talked about the physical meaning of the derivatives. If v sub t is talk about the position of object and t is time, so it means v dot t will be the velocity. Yes, that makes sense because velocity, it talks about the change rate of your position. If this means position. In general sense, because my vt does not mean it's a position, so it doesn't mean it's always the velocity. It just means the change rate of v sub t. So this means this is a change rate of position. Change rate of position is velocity. So some of the properties in terms of the derivatives, vector derivatives. Okay, I want to mention two important properties. The first one is you can scale your property, the vector up or down by a constant. So c is a constant. Okay, so derivative of c times vector vt with respect to dt is you can pull the c outside. Okay, c times the derivative of vt over dt. Okay. The second property is sum, the property of the sum. So if you do the derivative of the two vectors ut plus vt, and with respect to dt, it's the same as dut over dt plus dvt over dt, which means is u dot t and v dot t. Okay, so you can actually separate them. Okay. For example, if I have a u sub t, which is t plus 2t, and v sub t is t squared plus and t cubed. So dut plus dvt, you can put them together, right? Which is dut plus, if you put them together, u plus v. This is a vector sum, right? It's an entry-wise sum. So t plus t squared. So entry sum is 2t plus t cubed, right? If you do the derivative according to the vector derivative, is the derivative each individual component with respect to t. So it's a dt plus t squared over dt, which is 1 plus 2t. The second one will be d2t plus t cubed over dt is 2 plus 3t squared. Okay, so if you separate them, if you compute the dut over dt directly, so it just you follow the same rule. So it will be the first one, dt over dt is 1 and d2t over dt is 2. Okay, so dvt over dt, if it's calculated individually, you have dt squared, because the first entry dt squared over dt, which is 2t, right? The second one is dt cubed over dt is 3t squared. So if you put them together, it will be the same as this guy. So you can actually verify that this property is correct. Okay. So lastly, I want to mention a little bit about the curve, which means how to use a vector to represent a curve. Okay. The reason I say that is because I already mentioned somehow over here, because the axis of vector over here can represent a curve as you move along this circle. You actually put every point over here, you're actually trying to find the vector, right? Then you're trying to say, if I'm going to move from a starting point to the ending point, can I use a function to represent, to find every vector with any point on the curve, of course? And then I give a variable. If variable moves from some initial value to ending value, it will actually cover every point on the circle. That is called curve, a representation of the curve. So what I mean by that is curve, you actually represent a curve using vector function. Okay, what this means is, suppose that I give you a curve, let's say right over here, a curve. So I have starting point, I have ending point over here. So actually I want to represent every point on the curve by a vector, because I can actually draw a vector starting from the origin and to that point. I can get a vector for that particular point. So I want to swipe every point on the curve. Okay, what that means is I sort of say, if it's only for 2D, for example, I sort of want to find xt, yt. This is my vector. So if I let my v and my t actually move from t0 to tf, if t moves from t0, so I can have many points. For example, I have x t0, y t0, right? I have, so that, let's say this is the point I have. So it exactly represents initial point, initial starting point of my curve. I could have also x t0 plus very tiny one and y t0 plus delta t. So I move just a little bit. So it sort of have a second one, but somehow over here, let's see. Okay, right. This is my vector over here. So I can keep on moving, increasing t until it goes to tf. So this is a tf1. Okay, this is xtf. This is a y's tf. So actually, this is the point. This is a vector that I mean. This is a vector. I'm talking about this vector. So this is the last one you find. So if you move from t0 to t0, you actually continue moving along, then you cover every point on the curve. So this is what we call a vector representation of a curve. Okay, which means I have vector. Again, if I let it the variable t in the vector move from certain value, starting value to ending value, and all the vectors, all the ending point of the vectors for t moving from t0 to tf represent exactly cover all points on the curve. Then this vector is called a representation of the curve. Okay. All right. Let me give you an example showing a very simple example. Let's say I want to represent a straight line. Okay, a straight line means, oh, I have a straight line curve starting from, let's say, 1, 4, this point, and ending at 4, 5. So this is the sort of curve I want to represent. Okay, how do I represent that? My starting point is 1, 4, and ending point is 4, 5. Okay? So what I can do is, because the starting point is 1, 4, what an easy way we can do this is, Rt is 1 plus 3t plus 4 plus 1t. The reason I can do that is because, oh, this is my starting point. Okay, how to do that? So the starting point is, a vector is 1, 4 is my starting point. Okay? Alright, I know the slope. I want to find out the slope. The slope of this guy is just to be given by this ending vector minus the beginning vector. The ending vector will be 4 and 5 minus 1 and 4. So if I do this, you can sort of see, if I do them together, this will be just my ending one, because this will cancel out. What I do is, hey, let's do this time t. Okay, what I mean by that is, oh, if t is equal to 1, I know it's the ending point. When t is 0, I know it's become this point. So it becomes anyone in between, because this is the slope. This vector is the red vector. It's a red vector starting from here, ending at here. Okay, so this guy is exactly represent the red vector. It only represents 1 point if you do this one, right? Because it's one vector. So, but at any point on this line, actually exactly is part of this vector, right? So that's why I can scale this vector up and down, down until 0. It goes to this point. Once it is scaled exactly to the value when it's equal to 1, so it reaches this point. So if I scale it half, I just get this point. If scale it less than half, I get more every point over here. If scale it more than half but less than 1, so I get this point. Okay, that's why I can represent this one as this guy. If I let t less than 1 but greater than or equal to 0, that's giving me this exactly every point over here. Okay, so again, so this guy is the beginning point over here. And if t equal to 1, you get an ending point. So everything in between, so this guy represents another point over here. So that's why I see this guy is exactly over here, which is 1 plus 4, right? 1 and 4, right? This guy will be just equal to 3 and 1, right? This is the guy minus guy is 3 and 1. You time t, right? It's just 3t and 1t, right? So it will be 1 plus 3t and 4 plus 1t. Okay, that's exactly why I came from here. Of course, you can also do here is, you can say I'm doing it over here. What I also can do is, oh, I'm going to have 1 and 4 plus 4 and 5 minus 1 and 4. But I want to do this one divided by 2, which is not this vector, but this is cut by half. You know, you have this vector, right? Then you time 2t, you time t, right? And of course, if you only let t greater than 1, less than 0, it doesn't work, because you only try to cover all points from this beginning point to the half, right? Because it doesn't cover the second this part, right? If you let t to be greater than or equal to 0 and less than or equal to 2, you sort of can scale it up to this point. You cover every point over here. So this is also a valid representation of the curve. So which is exactly what I mentioned over here. Okay. So which is 1 plus 3 over 2t and 4 plus 1 half t if you let t to be greater than or equal to 0 and less than or equal to 2. Okay. So similarly, for the unit circle, we can also represent the unit circle. If I'm starting unit circle starting from this point and go all the way around and ending also at this point. So you can also represent the circle, assuming in 2D space, right? Which is RT, which is cosine t, sine t. The reason I can do that, for t is greater than 0 and less than 2 pi. Because if t is equal to 0, so I have RT, which is cosine 0, sine 0, which give us is 1, 0, right? Which is this point. Okay, because x is 1 and y is 0. So this is my vector. Okay. If you keep on let t going, it will just cover every point over here until you reach the end. So this is also a circle, representing a circle. You could also do this r sub t, which is equal to cosine t over 2 sine t over 2. You say t is greater than 0, less than 2, 4 pi. That will be the same thing, also represent a circle. Okay, that's all I have.